In this video, we will continue creating a two-layer SU8 master mold. In this process, the second layer exists entirely on top of the first layer, so it is not necessary to develop the first layer before adding the second layer. Furthermore, the soft bake for the first layer acts as the post-exposure bake for the second layer, albeit a non-optimal one. As before, we add the photoresist to the center of the wafer, covering about 1/4 of the radius. The soft bake starts at 65 degrees for a few minutes, depending on resist thickness, then a longer time at 95 degrees. You can start cleaning the spinner bowl while the wafer is baking, but be careful not to allow acetone spray from the bottle to land on the wafer. Run the spinner while squirting acetone onto the spinning substrate. Make sure the solvent waste reservoir behind the spinner does not overflow. After the soft bake, the resist layer is likely to be soft, but should not leave residue on your tweezers. As with the first layer, thick resist can get onto the back of the wafer. If this happens, the back must be cleaned by hand using acetone and a cleanroom wipe. Load the wafer into the center of the pattern writer, with the same orientation it had when you exposed the first layer. The DMO software should launch to the Align Wafer screen. Under the Wafers tab, set the current wafer properties to match your substrate. We are using the same 76mm or 3-inch wafer. Next, we need to focus onto the substrate. This is best done by typing in an expected thickness, turning on the manual checkerboard pattern, and using the mouse scroll wheel to move the microscope up and down until the checkerboard comes into focus. Now click the autofocus button, which is the icon with a small red triangle. The green progress bar beneath the autofocus button indicates that the autofocus routine has been successful. We begin the alignment process by finding layer 1 alignment marks and entering their expected positions. Our first layer has 3 alignment marks located at XY coordinates of 0, 0, 27, 0, and 18, 0. The orange tile button launches a feature that makes it much easier to find alignment marks. It does this by spiraling outward, taking pictures as it goes, and adding them to a mosaic image with a larger field of view. It allows us to find the center of the alignment mark without much effort. Double-click on the center of the mark to move the microscope to this position. The alignment window can be launched from the top left button in the Quick Access group. Under Marker Actual Positions, click the green down arrow. This records the current crosshair position as the first marker position. Now, under Marker Expected Positions, ensure the first set of coordinates match the expected alignment location of 0, 0. Clicking on the green Running Man button will make the microscope move to that position. In this case, it should move to the 0, 0 location from the first layer. Now we move to the approximate location of the 27, 0 alignment mark by typing in 27mm in X and 0mm in Y under Manual Stage Control. Once there, run the image tiling feature to locate the center of the mark. Once again, launch the alignment window and drop the second marker under actual position and record its expected position below as 27X and 0Y. Move the microscope to the expected position of the final alignment mark by typing coordinates into the Manual Stage Control. Run the image tiling feature to help locate the center of the mark, place the crosshairs at the marked location, and launch the alignment window. Click the third down arrow to drop a marker under actual position and record the expected position as 0x and 18y. The program now has enough information to transform the data file coordinates into wafer space coordinates. With 3 alignment marks, we can offset and rotate the data to fit the wafer pattern, but also compensate for a sloped Z-plane. The button to the right of expected marker positions transforms real space into wafer space. After clicking this button, Manual Stage Control coordinates should match wafer space coordinates. We check this by going to each mark and seeing that its location matches the expected coordinates. We now set up the data to be written into the second layer of photoresist from the Prepare Pattern window. We have already added 4 jobs to the job list. To add another, click the plus button under Job List, then click on the 3 dots to the right of File Name. This opens a browser where you can select your GDS data file. By default, this is placed with its origin at the origin of the wafer. Enter position coordinates in millimeters to move the job to its correct location on the wafer. The last window is for setting up the exposure. The resist sensitivity is the dose energy in millijoules per square centimeters and is always subject to some optimization. Global focus correction is the distance above the wafer surface that we want to focus the pattern. We have 2 layers of resist that are each about 50 microns, so we need a significant global focus correction. It is also sensible to do some optimization with this number. Under Tools, Focus Lock Options, we usually choose None under Real-Time Correction. Unlike our first layer, our data bounding boxes do not exceed the wafer area, so we can generate focus lock positions automatically. Start the exposure by clicking the green traffic light. As before, the machine performs an autofocus at 3 positions bounding the data. This is used to compensate for any tilt in the wafer surface. While the machine is writing the pattern, finish cleaning up the spinner. This probably means emptying the waste trap into the common waste container. When the wafer is finished writing, remove the wafer and perform the post-exposure bake. This is usually a bit shorter than the soft bake, but is very similar. This application of heat after exposure is necessary to complete the chemical reaction that cross-links the exposed photoresist. Development uses a hazardous solvent called PGMEA that dissolves the non-cross-linked photoresist while having much less effect on the exposed and chemically cross-linked regions. We use 2 baths of PGMEA and 1 dish for rinsing with isopropyl alcohol. Most of the resist removal is done by lightly used solvent from the squirt bottle. Just cover the wafer and agitate by gently rocking back and forth. You can use the spray to help dissolve any thick spots. Keep going until the resist is visibly cleared. This can take a few minutes. When the last bit of resist has cleared, immediately move the wafer to the dish of new PGMEA. Agitate here for about 30 seconds, and then move the wafer to the final dish and begin rinsing with isopropyl alcohol. You must rinse your tweezers to prevent PGMEA residue from staining the wafer where you grasp it. Blow dry the wafer with the compressed nitrogen and inspect your pattern on the microscope. To clean up, pour the heavily soiled first bath of PGMEA into waste. Pour the lightly used PGMEA into the yellow squirt bottle for reuse, and clean all dishes with isopropyl alcohol. Thanks for watching. Hopefully you're all done. But if your wafer has white streaks on it, it probably needs more development. If your features are wrinkled or bent, they probably need more exposure energy or less development time. If your features are lifting up in some places, you might need more exposure energy, a cleaner wafer, or more plasma treatment.